All right, let's dive a little bit deeper into this concept of like dissolves like. Up until now, we've been looking at like the kind of what is happening. We know the what, that like things dissolve in like things, like polar and polar, non-polar and non-polar, but we haven't really talked about why. And so let's kind of take a look at the process of dissolving something. So let's imagine we have a solvent and the solvent molecules are kind of close together. And we have a lot of solvent molecules because that's the major component. And we're going to take a solute, and I'll just use the kind of circle and the X there to represent the solvent molecules. Now, in order to get these to mix, intermolecular forces have to be overcome between solvent molecules with one another and between solute molecules, again, between one another. So somehow we have to kind of disrupt the intermolecular forces that are holding both the solvent molecules together and the solute molecules together. Now, both of these processes to, disrupt those molecules requires energy. So the delta H for that is going to be greater than zero, or that's an endothermic process. And it's the same thing for solute molecules. To get them apart, you have to overcome those intermolecular forces, which require energy. And then now what we're going to do is combine these and form new intermolecular forces between the solvent and the solute. So here we're forming new intermolecular forces. And this is a process known as solvation, the surrounding of solvent molecules around a solute, or the formation of intermolecular forces between solvent molecules and solute molecules. That's solvation. Sorry, this should be a greater than. That's a positive number. Um, and this process should be less than zero. It is an exothermic process. And so the amount of energy involved in this whole process of solvent molecules breaking up, solute molecules breaking up, and then recombining so that the solvent is now interacting with the solute can be described, or the energy required can be described with a delta H equation, where the enthalpy of mixing everything, or the enthalpy of the mixture, is equal to the enthalpy of solvation plus the enthalpy of breaking up the solvent molecules plus the enthalpy of breaking up the solute molecules. Now, these processes are already positive. Breaking up the solvent and breaking up the solute, as we said before, those are endothermic processes. And the solvation enthalpy is always negative. So when will mixing occur? Well, the requirement for that is that delta H of mixing is negative, so the whole process is exothermic, or it is possible for it to be slightly positive as long as entropy increases. And you'll talk more about that in 102. I won't go much more um, into that. And the reason that the delta H of the mixing is more negative, or the way we get that to be more negative, is with stronger solvent solute intermolecular forces. The stronger those are, the stronger the solvation is, then the more negative that delta H is going to be. So let's look at an example of this. Okay, so we're going to look at ethanol. So here's the Lewis structure of ethanol and how this interacts with water. Now, I'll kind of give you the answer first, and then we're going to look at the explanation of why this is happening. But ethanol is infinitely soluble in water, which basically means I can add as much ethanol as I want to water and it will always dissolve. It will never separate out. And the reason for that is that delta H mixture is a very negative number because there's a strong interaction between ethanol and water. Not only is there hydrogen bonding, so there's hydrogen bonding, but both molecules are polar, so they both have dipole-dipole interactions. And when two liquids mix together, they are said to be miscible. That's a term you should memorize. Just means that two liquids mix. If they don't mix, we call them immiscible. And then if we look at, for example, let's go to the other side of this and look at nonpolar molecules. So the compound hexane will dissolve well in a compound called benzene. Now, both of these are nonpolar. And so they only have London dispersion forces. And according to the like dissolves like, those are soluble in each other. So these would be miscible. Now, if I were to take, for example, hexane and water and put them together, so here's an example. We get a glass and put some water in it and then add some hexane to it. Even if we were to shake it up and let it, stir it up really well, eventually over time, the two things would separate out because hexane, as we said earlier, is nonpolar and water is polar. There's no way for the delta H of solvation would not be the correct sign to get water and hexane to mix. And so we would say these are immiscible. They do not mix. Now, one more example of this is why ions are so soluble in water. So, like for example, let's take table salt, sodium chloride. It's really, really soluble in water. Eventually, it does get to a point where you can't dissolve anymore, but you have to add a lot of table salt to water to get it to not dissolve. And the reason for that is you have positively charged sodium cations that are attracted to water. And notice how I'm kind of surrounding the sodium cations with the water. That's that process of solvation. And then the chloride ions are also solvated by water, but through a different way where they are attracted to the hydrogen of water. And that's why ionic compounds are, kind of get a little bit more specific later about in 102 about why some ionic compounds aren't that soluble in water, but um, a lot of ionic solids are very soluble in water for this reason.